So, welcome to this session about machine learning. The purpose of this session is to serve as an introduction to the topic of machine learning, and also at the same time to introduce you to the Scikit-Learn library, which is a Python library for machine learning. And so the session and the materials will weave in a little bit of discussion of what you might think of as theoretical topics in machine learning, introducing you to kind of the beginnings of the bread and butter of what machine learning is, and also code that demonstrates how to implement some of these ideas using Scikit-Learn, with the hope that you can take those examples and then implement them into things that you do subsequently. Priya, I see your hand is up.
Yeah, sorry. So I had not watched all of Elizabeth's video before the Q&A, but I watched part of it. Mm-hmm. And she was saying that Scikit-Learn doesn't work well for neuroimaging data, and that's why there's NeuroHackademy.
So yeah, well, we can talk about that. I'll start with some preliminaries that will include this caveat a little bit. How do you get your data into this format? And we're gonna brush that whole thing aside. I'll try to deal with that in the first few minutes here. Yeah, we'll try to deal with that. And of course, there are extensions and ways to deal with those challenges. So let me start things up here. Let me share my screen. And I will go to hub.neuroacademy.org, and you should have these materials available to you as well that I'm going to show once this thing starts up. Hopefully that won't take too long. So maybe I'll go in a little extended ramble here just to say machine learning is a very big field. And if we want to start defining maybe what it is that we're interested in here, is focus on looking at objective observations of the data and trying to extract maybe rules that we can apply then to other data. So where standard statistics is focused on inference, for example, what is the difference between these two groups, or what is kind of like a rule of this data. Machine learning is very much focused on prediction, on accurate prediction of the data. And prediction with low error. So that gets a little complicated because how do you define the error? What's good prediction, so on. But we'll see how you do that in practice as well. So I'll go into the curriculum folder, into machine learning. I'll start with these preliminaries. So I should say there are 6 notebooks here, and I hope that we get through most of those in today's session. So I'll go pretty quickly through things. Prerequisites, target audience, things are pretty minimal. We assume that you've seen some Python at this point, whether in a tutorial you attended NeuroHackademy or before that. All the code is in here, so you can run it and you can start tweaking things, things that are in uppercase or things that are particularly, things that are in capital letters are particularly amenable to tweaking and experimentation with that. There's some dependencies, but we don't need to worry about that because everything is in the hub. We will be using one data set. It's a neuroscience data set that we will be using in order to demonstrate the principles here. And this data set is taken from the ABIDE study, which is a long-running effort to understand autism. And the mechanism here is aggregation of many, many data sets from many different places. And the data is all stored in a tab-separated, TSV tab-separated values file within the repository. And so let's look at what that looks like. Here we're importing pandas in order to read this, this data. It's the function is called read CSV, but because it's tab-separated, we tell it to use the tab as a separator. And what you'll see here is that what we have here is each row in the data is an individual subject. And then there are columns that define characteristics of this subject. The first few columns here are what we'd call demographic characteristics, like whether this person has autism or not. That's group. The sex, age, and then it's taken from different sites. So that's why there's a site variable. And then the rest of the table are characteristics or numbers taken from FreeSurfer analysis of this data. So it's been run through FreeSurfer And we've extracted numbers out of FreeSurfer, like the area of the left V1 region of interest in this person, and so on and so forth. So these are all kinds of features of their T1 weighted data that were extracted using FreeSurfer and extracted into this table. So the table has a total of 1,004 by 1,446, so 1,004 rows, 1,446 columns. 1,004 is the number of subjects here. And then 1,446 is usually what we refer to as features. So down here we define there's samples, every individual subject in this data set in this case, but it can be in other kinds of data sets, it can be other things. For example, samples might be in some cases voxels, or sites could be a sample. It can be different units of measurement. And then these are the numbers that were extracted from FreeSurfer. Those we call features. So we think of this as a two-dimensional matrix. And two-dimensional matrices are the input to a lot of the stuff that Scikit-Learn does. So maybe that helps with the issue about neuroimaging. We've put all the neuroimaging data analysis aside here. We've done something with the neuroimaging tools, FreeSurfer in this case, to extract these features. And then everything else is fairly standard machine learning. You'll see what that means in just a few minutes. The really hard part is actually figuring out what features to extract. But we're gonna that has already happened and is very, very problem specific, very question specific. So we're not going to deal with that right now. But let's assume that you have a way to extract features from your data. Then there it is. You can use it in machine learning, and we should thank these folks, Bethlehem et al., for making these features available. I will say this is not entirely. It's not entirely divorced from brain data. It's not entirely divorced from the brain. You could go and plot how these different parcels relate to their locations in the brain. And if you do an analysis on these things, you can map that back to the brain space. And that's pretty much what this paper did very well, is showed how that goes back to brain structure. And there are some caveats here. It's approximate because this is volumetric and FreeSurfer is surface oriented. So it's a little, I've fuzzed it a little bit here, but roughly speaking, this is true. Okay, so that's the data we're gonna work with. And we'll come to some more caveats in just a minute. But let's start with some core concepts. So we will import a bunch of different Python libraries at the top here, NumPy, Pandas, Matplotlib for plotting. Seaborn is also for visualization. We're going to use that just a little bit here. And then we have a library of functions in here. Inside of support, we have a library of functions designed for this tutorial. And we're going to maybe import from that just this one plotting command. Okay. So let's talk about machine learning. What is machine learning? I started saying a few words about that before, and I'll elaborate that now. We think of it as a field of science, engineering. It's something between computer science and statistics, maybe, with a lot of applications to a variety of different kinds of data. And the main idea is that we're interested in building systems that are capable of learning from experience. And by experience, we usually mean we provide some data to the system, and we want the system to change so that it's able to produce accurate predictions on subsequent data or on this data itself. And one way to contrast that idea with traditional scientific or statistical inference is that our goal is less to understand or to explain how a system operates. We're less interested in introspecting the system, and we're really interested in very accurate prediction. So we prioritize accurate prediction over maybe producing results that are scrutable. So sometimes the results are inscrutable, and that's something we have to deal with. And we'll see some examples of that later on. And I should mention, these notes are all taken from notes that Tali or Coney wrote. And I should say, so sometimes you'll see here things that are funny. I take no credit for it. those goals are not mutually exclusive, as Tal points out here, but you need to often prioritize. They do lie in tension in some cases, and they're interesting ways to think about that. There are links from the notes here to papers that you can read that discuss this in much length. Okay, so taking this position for now of machine learning that we're interested in prediction, let's think about what different kinds of learning tasks we can do with machine learning. So one standard way of dividing machine learning is by thinking about tasks that are supervised tasks versus tasks that are unsupervised. And in terms of supervision, we don't necessarily mean how much we are controlling the learning itself. Rather, we really strictly mean only whether or not there is a given, in addition to the data that we're provided, we're given some kind of a label or a quantity that is associated with that, and use that in order to do our learning. Well, let's see what that means. We talked before about the kind of data that we get here. For example, all those subjects and their features extracted from FreeSurfer, that forms a big matrix, and we have samples by features in that matrix. Rows are samples, columns are features. And by convention, we label that matrix X. So in a lot of the code, you'll see X, and X refers to that matrix. But we might also have a vector of labels. For example, in the abide data set, we could have two kinds of labels. One label is whether that person was diagnosed with autism. So we have two different labels associated with people, diagnosed with autism or not diagnosed with autism. And we put that in a vector that we call Y. So that's a vector, and it has the same number of items in it. It's a column vector that has the same number of items in it as there are samples in the data set. That's because for every subject, we have one of these labels. So that's Y. Another kind of label that we might have is a continuous label. For example, for our abide data set, every subject has an age. And we'll look into age for you. So in that case, the Y is a continuous variable. It's not a discretely divided variable. Instead, it's a continuous variable that relates to age. Let's see how that plays into machine learning. Within supervised learning, when we have these labels associated with our samples, we might think about two different kinds of tasks. One is a classification of these discretely labeled items, and the other is called regression. So here's a very simple example of regression. Let's say that we have these data here. This is X is just one variable. So this is a case where our X has number of samples here is 30. So there are 30 points here. The number of samples is 30, and the number of features is actually just 1. And Y is also 30 values associated with each one of them, and we can plot them. So we can plot the X values, the Y values as a function of X, and we get this scatter plot. And we can frame this as a regression problem by saying we would like to be able to predict the values of Y based on the values of X for every individual. And one way to do that is called ordinary least squares regression. It's linear regression. Here we're solving linear regression quite explicitly. So here's how that works. We have our X here, our X variable. It's just remember, it's one feature with n samples, 30 samples in it. In order to do regression that includes both the slope and the intercept, we need to add one more column to this X matrix, a column of 1s, to create the intercept term. And then here, this is solving least squares regression explicitly. So this is inside of NumPy. There's a linear algebra library that has a solver for least squares. When we give it X with the intercept and Y, it goes in and estimates this straight line here that goes through the data. And that's the solution. And it also tells us, we estimated parameters along the way. So this W here are the parameters. And it tells us, oh, you have an intercept of negative 0.36. So if you look right here at 0, this value of Y at which X equals 0 is negative 0.36. And then the slope is 0.62 for every unit of x that we go, we'll go 0.62 units of y up. So that's our linear prediction equation that produces a predicted score for every x. We can predict a score of y here. So that's a regression problem because y here is a continuous set of values. Another kind of problem we might have is a classification problem. So in this case, we have values of x and values of x1, I should say, and values of x2. So in this case, x has two features, right? In this case, this may be a little confusing. The y in this case are the colors of the dots. And x has two values. So for example, x1, which is the x-axis in this plot, the first axis in this plot, if the values of that are low, it tends to be blue. And x1 or x2, sorry, the y-axis on this, when the values of that are high, it tends to be yellow. And the kind of task we might do here is we might look at the values of x1 and x2 for every point here, for every sample, and we might say, is it blue or is it yellow? In this case, it's pretty easy to classify them because they're well separated. If we made a rule that was maybe a straight line that goes through here, through the middle of this, we might get accurate classification. And we call that, because we could draw a straight line through this surface here, that would give us a separation, a neat separation between those two. This kind of problem is called linearly separable, because you can correctly classify 100% of the samples just by drawing a straight line between them. But that's not often the case in the real world. Here's maybe a more realistic situation like that, where there's things that are mixed. So now there's no straight line that we could draw through here that would cleanly separate, that would separate 100% of the points. And that'll be in most cases in the real world, you'll find things like that. And then you might maybe draw a straight line or something that is not quite a straight line through this in order to separate as well as possible, so that your accuracy in separating and classifying these points is as good, as high as possible. And things get really, really interesting, or a lot more challenging, and maybe more fruitful when you have very, very high dimensional problems. I mentioned, we went here from one feature per sample to 2 features per sample, and usually we'll have many, many features per sample. In the case of the BI data set, for example, we have 1,400 and something features per sample, which makes for quite an interesting situation. And often you'll see maybe problems like this one, where you're trying to classify multiple different classes and things are very mixed within each other. And in this case, it's not exactly clear what the answer should be even. Are there 5 different classes in this data? So things get a little bit, can get a little bit complicated when you're doing that kind of work. Okay, let's see. What questions do people have so far about supervised learning and any of the settings that I've set out so far? So I'll keep going. Unsupervised learning is another form of learning. In that case, we don't necessarily have a label that's associated with every one of the samples. For example, look at this data. Maybe they're not colored in for us, and maybe we're trying to figure out from the data whether there are natural kinds in this data set, whether there is a way to split this up into separate labels. And we're trying to color in labels where no labels exist in the data originally. So it's not so much about learning the separation between classes that are known, rather it's about figuring out whether there are natural classes in the data. And that problem is an unsupervised problem, and that's because there are no labels associated with that. In particular, when we're trying to associate a label with every group of points here, figure out how many groups there are and associate color with each one, then we call that clustering, because we're trying to find clusters in the data that neatly sort of group into groups. So in the case of clustering, our goal is to label the samples into discrete clusters. And as written here, clustering is classification without ground truth. So we don't have ground truth to rely on to train the algorithm. Instead, we're training the algorithm on the structure of the data. So here, that's very easy to do. There's no colors associated. So we use this make blobs function up here from Scikit-Learn. Scikit-Learn has various functions to create synthetic data, and we use that function here in order to create these blobs. But we're ignoring the y here. Instead, we're just plotting the x's. So that's every x here. Every sample here has two features, x1 and x2, and we're putting them down into the space. And in this case, it would be easy for us to say, oh yeah, this looks clearly like three different things are here. So we don't know the true labels, but we could guess them. If we guessed something like that, that would be a pretty good guess. And there are algorithms that do that for us. Of course, the situation is often more like this, where now it's much harder. So maybe this is ground truth, and this is what we see because we don't have the ground truth labels in this particular data. We can imagine some neuroscience problem where you have maybe a group of subjects and you'd like to split them up into different kinds. Maybe what you see is like that, and what the ground truth is like that. So that makes it much harder. Not only do we not know who belongs to a cluster, we don't even know how many clusters there are in this data. We don't know the fact that this came out of three different things. So that's the problem that we face when we're doing clustering. Another kind of unsupervised learning that's not entirely unrelated is when the data itself, the variables themselves, let's say that we have a data set where we have multiple features, maybe those features are not entirely unrelated to each other. That is, they're not drawn independently from the world. Instead, those data are somewhat related to each other in a way that feature 1 and feature 2 are not independent. Instead, they have some dependency. And so another form of unsupervised learning is called dimensionality reduction. In this case, we're trying to take a data set that has very high dimensionality, and we're trying to compress that dimensionality down in order, again, to establish what is the structure that exists in the data. For example, what are the codependencies between different features in the data, to maybe make the data more comprehensible. We could do that also for purposes of things like denoising. We'll see later how we use that as a step in an analysis pipeline. So, for example, here's a dimensionality reduction problem. Consider this data set. So this is a data set that has two variables. In this case, we generated this data sort of like a regression problem, but consider this to be x1 and this to be x2. Nominally, this is a two-dimensional data set because there are two variables here, right? Every point here is a sample. Every sample has two values associated with it. And nominally, this is a two-dimensional data set. But in fact, if you know the value of one feature of the data, you know with pretty high confidence the value of the other one. They're really, really strongly dependent on each other. And that means that this data doesn't really have two dimensions. It has something slightly less than two dimensions in the sort of linear dependence sense, or even in sort of in terms of the information that exists in this data. And so you could reduce this down by saying a lot of the variance here is on the first dimension, and there's a little bit of variance on this second dimension. A lot of variance is on this dimension that combines these two features together into one feature. And then there's some variance on this other one. And that's called principal components analysis. And we'll look at that in a little bit more detail later on. Ben, I see you have your hand up.
Yeah, this might be just another version of exactly what you're saying, but can you ever do dimensionality reduction when you figure out that one of the dimensions is completely meaningless and gives you no information at all?
Yeah, 100%. Yeah. That's yes. Let's say that you have a variable there. I'll try to sort of paraphrase your question. Let's say that you have a variable in there, and it's completely noisy. It's really not giving you any. It's not related to any of the other variables. You might say, well, this variable is somehow not related to. Well, no, this is actually a bad example. Because if it's unrelated to any of the other variables, then it has its own variance that we should account for. So
right, that's exactly my question, is if it's unrelated to the other variables, but also unrelated to your y, are you ever able to confidently reduce that out?
Okay. So now you've gone into the supervised setting.
I'm sorry.
In the supervised setting, yes, that does happen. You might have a variable that's you have 1,000 variables, and some of them are just completely unrelated. For example, in a few minutes, we'll see how you predict age from those brain features. And maybe there's some feature that just doesn't change at all with age, doesn't tell us anything about age. And yes, one of the goals of machine learning is then to squeeze out that variable and reject it as an explaining variable for our supervised case. In the unsupervised case, the thing that happens is that a variable can be completely redundant with other variables, and then we squish it out. So for example, imagine that we had a third variable here. So we have x1, we have x2, and imagine that we had a third variable that was a linear combination of our first two variables. In that case, the true dimensionality of this data would at the most be 2. Because this third one is completely explained by these other variables. So that's kind of the opposite of that. It's the opposite of actually what I said before. If you have a variable that's completely independent from these other variables, that variable does contribute interesting variance to this data, and we need to account for it. But if it has no additional variance that's not explained by these first ones, we can squish it out, and that's kind of like the dimensionality reduction aspect of this. And maybe it's linearly dependent on these two first ones, but has tiny amount of noise on it. We can also identify that case, right? To say, okay, it's mostly explained by these two variables. So it doesn't add a lot on top of these two variables. And then the question is, well, how much do we want to reduce? And that becomes a little bit of a judgment call. Okay, so now you've seen sort of a little bit of the galaxy of different options that exist in machine learning. Just to kind of recap, we have supervised learning. Within supervised learning, we have the case of regression, where the labels are continuous. We have the case of classification, where y is discrete categories. And then we have unsupervised learning. One kind of thing we do is clustering, where we split the data up into bits. And the other is dimensionality reduction, where we try to squeeze the dimensionality of the data down in order to extract the main structure that exists in the data. What questions do people have at this point? Okay, so let's go back to the abide data and try to do something practical with this. Here's the data again. I've read it from this TSV file, and I've shown you the first few rows in this. So remember from before that the data frame contains 1,004 rows and has 1,446 columns. The first 6 columns here are phenotypic variables, and age is one that we're going to focus on a lot, measured in years. So this is age in years at time of scan. And then there's diagnosis, which is the group where 1 indicates an autism diagnosis and 2 indicates a control subject. And there are other things here. But the rest contain 4 sets of structural brain features, the area of different regions of interest, the volume of different regions of interest, cortical thickness within those areas, and local gyrification within those. So we have 360 variables times 4. And so let's see, this is the parcellation that I showed you before. So these are the different parcels to which these features, the 360 regions of interest are in here, and then so these are these different parcels, and so that's what's associated here. And so we're going to use those variables. We're going to basically cut out this part here, and we'll call that X later on. Let's for a second take a detour here to talk about Scikit-Learn. So we're going to use Scikit-Learn here. Scikit-Learn is, I'd say, a very influential and dominant package for machine learning. It's been in development for many years, and it was really established itself as kind of like a standard of how to do machine learning in Python and more generally. Some of its popularity stems from the fact that the interfaces, the programming interface is just super elegant. And you'll see what that looks like in just a minute. It has very good documentation, including multiple examples, worked out examples of different kinds of problems. It has, I'd say, the benefit that it is fairly conservative. And by conservative, I mean that Scikit-Learn implements only methods that are really, really well established in the machine learning literature. And that means, from the point of view of somebody who is interested in exploring machine learning, that means that when a method is implemented in Scikit-Learn, you can trust that that method is a useful method in a broad range of use cases. It's been explored thoroughly and taken up by the machine learning community. So now what we're going to do is we're going to convert our data into the kind of shape or form that the Scikit-Learn library expects. So we're going to filter our data. This is our pandas data frame that has the data. We're going to filter it to only take the columns that have FS in their name. The way that this data was organized is such that just the features from FreeSurfer have FS in their name. And so here is X all is just those columns that have FS in their name. You'll see it's basically everything but those first 6 columns that contain phenotypic data. For unsupervised learning, as I mentioned before, we only need the feature data, just the X, just these data. But for supervised applications, we're going to want also some Y, some label. So in this case, we're extracting the age as Y. So this is the data. We're taking the age column, the values. So notice that the way that we've extracted it, the order of the rows for the X and the order of the rows for the Y is matched, so that the first row of Y corresponds to the first row of X, and so on. Every subject has the data, so we can combine those data together in various ways. Let's start with sort of a fairly standard thing to do here, is a brain age prediction. So what we're going to do is we're going to create a Scikit-Learn estimator object, and we're going to use that estimator in order to do regression, which is a supervised learning algorithm, between the FreeSurfer features and the age. As mentioned here, one of Scikit-Learn's most attractive features is its unified, simple interface that allows us to configure estimators and fit the models. So there's a basic kind of object in Scikit-Learn called an estimator object. And that object implements methods, one method called fit, another method called predict, and there are other sort of standard methods that come along with that, but we'll focus on fit and predict first. One of the beautiful things about Scikit-Learn is that when you initialize one of these objects, it comes to you as a generic container, and you separately need to apply the fit method on data in order for it to do the fitting itself. So you can configure it, and then you can use it. And those two steps are separate from each other. And then once you fit it, you can apply the predict method to create a new prediction of the label, of the outcome. Let's see what that looks like. I'll make that really, really concrete with ordinary least squares regression. So here we're doing, notice that this is in capital, so this is something that you can play around with. What we're going to do is we're going to fit a regression model. We're going to predict age as a function of 5 features from that set of features sampled in random. So we're sampling here X. I'll actually print out X.shape and Y.shape. Right, so this thing here is our X matrix. It's got 1,004 rows, 1 for each sample. It's only 5 columns that we've selected in random from among the FreeSurfer. And then the Y is 1,004 for all the subjects. Okay. Next, we import and initialize a linear regression model. So this is the first time that you're seeing a Scikit-Learn estimator. The linear model module in Scikit-Learn includes an object called the linear regression object. Here we're initializing that object. And linear regression, there's not a lot of configuration to do with linear regression. One of the things that you can do here is decide whether you want to fit the intercept or not. If you fit the intercept, it'll fit one more variable for accounting for the intercept, and that's true per default. So we don't need to actually even explicitly mention that. Next, so notice what I said is this: we configure and initialize the object separately from the fitting itself. At this point here, the model hasn't seen any data. It's just kind of like a notional container that knows how to fit data if we were to give it data. So that's what we do next. We call the fit method. And at this point is when the actual fitting happens. Before we did this, the model didn't have any coefficients associated with it. It didn't have any intercept associated with it. But once we called the fit method, it has an intercept and it has a set of coefficients. Here we're printing them out. The estimated intercept is 53.81. That's age in years. And then the estimated coefficients are written down here. And there are 5 coefficients, one for each column that we fit. I'll make this really concrete by going back here and just pointing out that if I initialize this object again, I run this again, and I ask what is the coefficients, it'll say I don't have this attribute coefficients. That's because I haven't fit it yet. It's only down here when I call fit that the coefficients come into existence. Scikit-Learn has a special way of designating these kinds of variables. In statistics, sometimes people call these exogenous variables. These are variables that come to us from the data that only exist once we have seen the data. It designates those with an underscore after the name. So you'll see here that intercept has an underscore after its name, and coef has an underscore after its name. And that just means these are variables that came to us from the data. We had to see some data in order to initialize these variables, and they didn't exist before we did that. You'll also see these coefficients. We sampled some 5 random features from this data, and these coefficients vary quite a bit in their magnitude. This one's almost 9, while this one's like negative 0.01. And that's because the scale of these different variables is quite different. One is area of an ROI, another might be cortical thickness, another one, I don't even remember, but they're quite different from each other. So they're not, the fact, in and of itself, the fact that these coefficients are very different from each other is not a very interesting fact. It doesn't tell us much about sort of the importance of these variables for the prediction or anything else. And that is really the next thing that we'll do is we'll generate a prediction here. So we can invert the process of fitting the model by generating a prediction. So here's what that looks like in math. We have these coefficients. 53.81 is the intercept. And then we have these different coefficients associated with each one of our different variables. Notice that the 4th variable here disappears. X4 disappears, and that's because its coefficient is literally 0. So we never look at it when we're doing a prediction. But this is the way why the hat here designates that this is a prediction. If we were to predict something, we'd take its x. We take so let's say that we have a new sample or a new set of subjects, or even the same set of subjects that we had before. The y hat would be our way of taking their properties and trying to predict based on the fitting that we did. And that's what happens right here. Model.predict, and we give it x. We give it the features of the subjects, and this one will be our ypred. And ypred, the shape of that is, again, 1004. It's exactly the same size and dimensions as the original y. And we can visualize that by plotting the predicted age against the true age. Here we used Seaborn as the visualizer. We've plotted ypred, y, and we've set some axis labels here. So we have age predicted, age true, and you can see it's, it's predicting some, but it's missing a lot. So, there's, as mentioned down here in the notes, the model appears to be capturing at least some signal in the data, in that, there's some non-trivial relationship, but clearly the relationship is not very linear, right? The straight line here is not a very good model of this data. And we can do various ways to address this. One that's suggested here is to apply a transformation to y before doing the fitting, and then try to invert that transformation. We could log transform the age, for example, and repeat this. But let's not worry about it now. We're interested in learning about machine learning scikit-learn, not to produce publishable results. But let's just celebrate for a second the fact that in just a few lines of code, coming here from initializing the linear regression, fitting the data, and then predicting, we've gone from, we've fit our very first model. Here's the whole example in 3 lines. Model, initialization, model fit, model predict. And that's it. We went from data to prediction. Let's see, what questions do you have so far about this process? Okay. If no questions, yes, Shelby, I see your hand.
Yeah, I guess I had a question. It's not necessarily about the machine learning aspect, but kind of touching on like if you were to maybe use this for like NeuroLearn and thinking about the meta-analysis, like the regions of interest that were identified earlier. So like, let's say, I'm looking at all of these different meta-analysis, and I see like my region of interest is maybe like this region or something like that. But like the identified regions are maybe not like what I would have considered like part of that region or something like that. Like, how do I know like what regions to identify, or how do I know like from that data set maybe like where those are coming from, if that makes sense?
Yeah, in this case, when we did this, we just randomly selected 5 columns. But you'll see in just a bit that we're gonna try to boil the whole ocean here. We're gonna try to run this with all of the data in there. We'll run into some trouble. We'll try to figure out how to run out of trouble as well. In the end, we'll get to your problem where we identify, we say these regions are important and these regions are not important. And what do we do with that then? And that's it's a tricky question, because it depends a little bit what you think, how much you believe this model, what your interpretation of these results. For example, if you're building a model that predicts age from neuroimaging data, there's by now a big literature that looks at that particular problem and has defined a lot of issues with that problem, a lot of the assumptions that go into that. Be that as it may, for any particular problem that you're doing, be it brain age or something else, there is something very informative about there's something interesting and useful, potentially useful, about the fact that certain variables are selected as informing this thing. And depending on the scientific nature of the measurement and the problem that you're solving, this might be quite interesting and illuminating, or it could be a confound with something else. So it's very question specific, not general for this.
Awesome, thanks.
So, okay, here, oh, sorry, what other questions do people have at this point? Okay, so I'll keep going here a little bit. This is just a little interlude here to point out that machine learning is not usually about inference over the model parameters. If you've used things like SPSS or R and you've run kind of inferential statistics, you might have seen something like this, which is also ordinarily squares regression, but seen from through the lens of inferential statistics. What we did here is we looked to another modeling package in Python called stats models. Stat models implements ordinarily squares regression. In this case, we're again setting up the X matrix for that. We're giving it Y. The API is slightly different, but the results that we get out are more in line with maybe what you're used to seeing in traditional statistics, where we get an R squared for the model, an adjusted R squared adjusted for the degrees of freedom, an F statistic, the p-value, and then for individual coefficients, their values, their p-values, and we're in a confidence interval. And you might look at that, and that's also an interesting thing to do. Note here that yeah, there are sort of caveats here. The condition number is very large, which might suggest multi-collinearity or other numerical problems. And there's the standard errors assume certain assumptions about the errors in their distribution and so on. So there's things that come along with this, certain assumptions that come along with these tables and their p-values and the p-values associated with these coefficients and so on. But that's not what we're doing here. So we're gonna move on from that. Just to point out, it's not entirely a different thing. It's very similar, but the kind of the way that we interpret things is maybe a little bit different. Instead, we're going to focus very insistently on performance in terms of prediction. And so one way for that, you need to define your metric. How do I know that it's predicting well? One way to know that it's predicting well is to measure a measure of error in prediction. There are many kinds of measures of error. One that's really popular is the coefficient of determination, R squared. One interpretation of the R squared is the proportion of variance in the outcome variable that is explained by the fitted model, by the model that you fit, so that you can find in the predictions. So here we're getting R2 score. Here we're getting the R2 score from the Scikit-Learn metrics sublibrary or submodule, R2 score. We're doing the prediction here, and then we're comparing Y to Y pred. That's the order in which it comes in. And we get a number. And what this number tells us is that about 20% of the variance in the original Y is explained by the Y pred. It's a way to quantify this scatter plot. Like how good is this scatter plot relative to a scatter plot maybe where the points are closer? Well, it's a 0.2 relative to, if this was just a straight line where error prediction would match accurately, we would get a 1.0. That's all the variance is explained. So 0.2 is the number. And, depending on your problem, that might be good or it might be not so great. But it's a matter of perspective. But, at least we know it's not 0. Which means, there's some variance explained. So that's interesting. And as an exercise, you can try putting in other kinds of metrics. There are a variety of metrics inside of this library that you can put in here. But just moving on one more cell before I turn to Matilda's question, I'll just point out that the estimators, so here's an estimator in Scikit-Learn. It's the linear regression estimator and has a fit method with X and Y. It also has a scoring method, which given an X and a Y will give you the R2, the R squared metric in this case. The scoring method for the appropriate scoring method, according to the developers of Scikit-Learn for linear regression, is R2 score. And that's the score that you get when you do estimated.score. Okay, Matilda, I see your hand.
Yes, just one quick question about these R2 score. I know it can be negative, and so I'm always a bit unsure about the values that this metric can basically have, and what's the kind of relationship with a correlation coefficient, for example.
Right. It looks a lot like a correlation coefficient, but it is not a correlation coefficient. Yeah. We can write out the equation here, but maybe that's not too. It really is not. It's not the Pearson correlation coefficient, although both of them are referred to when you write them as an R squared. It's also confusing. It can in fact be negative, and it's called R squared. So you look at that and you're saying it's a squared number. How can it be negative? That just hurts my head. So maybe ignore that for a second and just consider the following. R2 score is a number between negative infinity and 1. When it's 1, that means, for example, if I were to, let me manipulate this a little bit here. Y with Y itself is going to be 1.0, right? If Y prediction is identical to Y, that's perfect prediction, and you get 1. In this case, Y pred is not, so, but let's say that I added some offset to this. Then it goes negative. And the reason for that is that the prediction is way off. So the one way to think about this with relationship to the Pearson correlation coefficient is that the Pearson correlation coefficient is bounded between -1 and 1. And the reason for that is that we're given one more degree of freedom. We're allowed to shift the whole thing up and down. we're allowed to shift the whole thing up and down so that we get the best match between the two variables that we're comparing to each other, y and y pred. If y pred is off by 1,000, we're allowed to subtract 1,000 to bring it back. And that's, if you remember the definition of the Pearson correlation coefficient, each one of the variables separately removes its mean. And that's the allowance that we get to remove this offset. But here in our 2 score, we're not allowed, we're not given that additional degree of freedom. So if the prediction is off by a lot, that there's a big offset in the prediction, the score will be bad, regardless of if the slope is good between those two. If the mean prediction is off, it's off. One other way to think about this is that our 2 score is a comparison of the model that we have, this linear regression model, to an alternative baseline model. The alternative baseline model is to predict the average value of y for every value of y. So that's a baseline model. We saw y, and we're always going to predict the average of that, of those values. That has a value of 0. So everything better than 0 is better than predicting the average. But notice here we're predicting really far away. So we're predicting way worse than we would if we were predicting the average. I'll just demonstrate that by doing np.mean of y. I think it's np1's y.shape. So I need to put that inside of it. That's exactly 0. So if I predict the mean for everyone, I get 0.
Okay.
So that's the R squared score.
That helps. Thank you.
Sure, yeah.
Thank you.
What other questions do people have at this point? All right, let's go to one other kind of example here. We're going to do another kind of example here with this data. This is going to be a classification example. So the data includes also these labels for subjects that have been diagnosed with autism. Now let's take a look at this. So, here Tal has cleverly selected 3 variables that do kind of correlate with the autism label. And he's displaying here, we have the 3 variables, our x's are here on these axes. And then the color of each point here, there are 1,004 points here, and each point here is colored according to the diagnosis. And there's a little interactive widget here, so we can turn it around a little bit and try to see whether, if we look at that, if we see a clear way to separate yellows from blues here, I'd say it's really hard to do. Just from there's maybe some points out here that are sort of separated out from the cloud, but it's just really hard to do in this data. So that's interesting. And let's see if we're able to do that anyway. So how do we apply classification estimators in Scikit-Learn? Well, it's a trick question. It looks exactly the same as the previous estimator. And that's because they all have exactly the same API. So here is the full classification problem. Now we're we're importing another kind of estimator object. This is also an estimator object. The linear regression object was an estimator object. And Gaussian naive Bayes classifier is another Scikit-Learn estimator. Here we're initializing our Gaussian naive Bayes object. In this case, we're extracting y, which is the group, and then we are fitting that to this x-all. And remember that every object in every one of these estimator objects has a fit method, it has a predict method, and it has a score method. So we can, instead of predicting and then comparing the prediction to the true and so on, we can go straight to the scoring and score that. So then the question is, what is this score? Is 63%, is that good or bad? And that, as always, depends a little bit on how you score that. Instead of using the score, you could generate what's called a classification report. So in the metrics, there is a classification report, function. So here's now we're generating the prediction indeed by calling predict from this Gaussian naive Bayes predictor. with the x's. So this generates a y hat for us. That will be 1 or 2 for every subject. And then we will create a classification report of y pred, similar to how we did with the R2 score. But here it gives us a little bit more. It gives a variety of different metrics. It gives us for the labels 1 and 2, it gives us the precision, as in, you know, how many of those that truly are 1 are given the 1, but we also get recall, F1 score, and the support. The support is the number of individuals in that. And then you can go and you can get, you know, the macro average, a weighted average by the number of samples, and then recall and F1 score for those as well. So you can see that while the precision is almost identical for the two groups, the recall differs substantially. Control subjects have a higher probability of being correctly labeled than do subjects with an autism diagnosis, which is interesting. And I wonder if you can think of explanations for that given this. Yes, Ben.
I'll hold off on this question if you're going to talk about it later. Are you going to talk about multi-class classification and classification reports?
I don't think so. And I don't,
okay.
I'm predicting that I don't know the answer to your question. But your question is pretty much like,
Well,
okay, I have a multi-class problem here.
Yeah, my issue, you know, I do a lot of natural language processing, and I have a lot of, you know, negative, neutral, positive, and I always have a lot of trouble, you know, evaluating the performance because I don't get nearly as much detail. And I'm just wondering if you have any general advice on that.
I don't. I'll need to think about that.
Or if anyone does.
Maybe let's take that offline separately. I'll try to think of something clever to say about that in the meanwhile. But in the meanwhile, let's look at this. So do you have any thoughts about this little weird asymmetry that exists here? So this 78% means, you know, these are the subjects that are 2s and are correctly labeled as 2s. Out of 2, how many are correctly identified as 2? Their recall is 0.78. So I think, you know, if you look at this, there might be, Matilda, you have an idea or a question?
Yeah, sorry, question. I was just kind of stuck on thinking how to pick the classifier. I mean,
how to select which classifier?
Yes.
It's a little bit of trial and error.
Okay.
In this case, this was selected as it's Gaussian base is a good baseline estimator. It works a lot of the time because it sort of relies just on the natural distribution of stuff.
Yeah.
Pretty well. And you know, it sort of assumes that the variables that you selected are useful and they're independent of each other.
Okay, thanks.
Conditional on the class assignment. So
I was just wondering whether based on.
But there are a lot more sophisticated classifiers. I guess.
But would it be fair to select the classifier, for example, based on the performance that the classifier says?
Yes, we'll come to that next. Yeah, that becomes an issue soon. Yes, yeah, you could do a little bit of experimentation to select a classifier based on its performance, with some caveats. So we'll see that in a second. So one thing to think about here is like how heterogeneous are these different groups? That might be one explanation. Another is to look at their different support. That might be another way to explain these differences. Be that whatever that is, we'll not explore it much deeper, but let's go instead to one more example. Shelby, I see your hand.
Yeah, what is support in that last column then?
It's the number of, I think it's the number of observations in each one.
Okay.
Yeah, it's a fancy machine learning word for n. Yes, Isabel.
Yeah, could class imbalance also cause a difference in the accuracy of the classification?
It can, yes, yeah. The class imbalance can tilt things quite a bit, right? The classifier will say, well, I see people not diagnosed with autism much more often. Let me just choose that. If I don't know what to do, let me just say this person doesn't have autism because they're more common. Yeah, that's sort of you're building a bias into the classifier. Maybe that bias is justified, right? You think about the base rate of some disorder. It might be a good classifier for a very rare disorder is to never diagnose that disorder, right? In some sense, right? It's accurate a lot of the time. It's just when it's inaccurate, it's catastrophically inaccurate. So it gets a little tricky because it's not clear that these kinds of metrics are really what you want to measure here. If you're trying to diagnose a rare and very dangerous disorder, you want to be able to detect it when it's there. So that kind of set of considerations also plays into this. And it makes it very tricky to build a good classifier that will do that, because a lot of these classifiers will just do will optimize on the wrong metric. They'll optimize on one of these accuracy metrics. So it becomes tricky. Did that answer your question?
Yes, thank you.
Okay. Okay, let's move on to one more example here, which is to do some kind of unsupervised learning here. You'll remember that clustering is a form of unsupervised learning. In this case, we're going to demonstrate how we split up the group, the subjects in this sample that have a diagnosis of autism. We're going to try to see whether there are natural kinds within that group that we can separate out. So here we're going to use a few different things that we haven't seen before. We're going to use the scaling preprocessing. The Scikit-Learn has a set of preprocessing tools. We're going to use the scaling preprocessing tool from here to standardize our columns within every feature. We're going to remove the mean and standardize the variance to 1. So that's the scaling. We're going to, in this case, just randomly select 2 features for this. And here we're selecting only the autism group by selecting only those individuals that have in their group the number 1. And then, the nice thing about this is, again, the API is exactly the same as you've seen before. We find the method that we'd like. In this case, it's k-means clustering. Here we're going to stipulate that k equals 4, and then we initialize the object. In this case, we initialize the object with some configuration. So before, when we initialized our linear regressor, when we initialized our Gaussian naive Bayes classifier, we didn't have anything inside the parentheses. But in this case, we are parameterizing that. So it's a k-means clustering object that has 4 set as its k. And then we're going to run fit predict, which runs fit and predict in one shot to get our clusters out of that. So this is, notice interestingly, there's no y here. dx1 is the two features that we selected from x. Y never, there was no y here ever, because we split the data by this autism group. We split the data into 2 up front, and then we're only operating on one of these groups. But at the moment of the fit, there's no x and y here. There's only x. And that's because this is an unsupervised learning approach. In unsupervised learning approaches, there's only x. So we're no longer passing a y array. Here are our clusters. So we stipulated up front that there are going to be 4 different clusters. K-means, the way that k-means operates, it kind of finds values of these 2 variables around which you can aggregate clusters. It kind of moves where those averages are until it finds a good, stable solution for that. And so, this first one was closest to one of these means, and this 4th one was closest to another mean in terms of the values of these 2 variables that were selected for clustering. We can visualize that right here. Okay, so this is a visualization of Why is this not expanding? I'm not sure. But this is a visualization. I'll have to scroll back and forth a little bit. This is a visualization of the results. So this also demonstrates a little bit of what K-means is doing. It's trying, having told it that there are 4 clusters here, it tries to find these centroids, these 4 centroids. It starts with some initial conditions, and then it starts moving these centroids around until the error, the overall error or the overall distance of the points from centroids is as small as possible. And then it stops. And then every point here is colored according to the centroid to which it's the closest. That's the K-means clustering algorithm. And there are other clustering algorithms. And it operates only on these 2 variables. Remember that we randomly selected 2 variables here for the clustering. And we look at that, and these points are indeed closer to this. But looking at this, it's kind of hard to say whether we've really found neural subtypes of autism based on this data. Is this truly the place that you would put the difference between this cluster and that cluster? Kind of hard to say in this case. So maybe it's not a great result. But that's the kind of evaluation you want to do. Yes.
So sorry, do you mind if I ask a quick question about
go
this?
ahead.
So I always wonder when it comes to clustering about a few things, and I was wondering if you could help me find some intuition for it. One is, I guess, how to define what is a good number for the clusters, and how to, I guess, find some sort of way of verifying that you found a good one. And then also how to think about the distance between 2 points and how that's meaningful, a meaningful distance metric, and how to find that.
Those are great questions. Let me start with the first one. The next few things that we'll do here, and I'm going to try to speed up, is to try to sort of reconcile all the issues that we've seen so far about evaluating these models, about figuring out, is this a good description for the data? And I hope that it'll also encompass this clustering problem. We need some kind of objective metric that will tell us, obviously within this data, this is and given 4 clusters, this is the smallest, the solution that gives the smallest error in the sense of the sum of the distances of points from cluster centroids. But if you think about it for a second, if I were to add 1 more cluster in here, that would, per definition, do better in this, the error, because we'd have 1 more point here, and we'd plop it pretty much anywhere we want here, and the errors are going to go lower by definition. So that's not satisfying, because if we continue with this logic, we'd end up with just number of clusters is number of points here. And so we want some kind of parsimony, and we'll see how that trades off, this kind of parsimony. So there's sort of a general principle here, which is Occam's razor. We want a model that is as simple as possible to account for the data we see. And we'll see how we enforce Occam's razor in a quantitative way when we're doing machine learning. So that's regarding sort of how do you do this mechanically. And then the other question was regarding interpretation of clustering results. Is that right?
I was wondering about the distance metric and how that's meaningful.
Yeah, so that's really tricky and is very specific to the particular problem. Here we've defined a Euclidean distance, right? The distance, when I said distance, I meant Euclidean distance of these points from here. And this is a Euclidean distance in the space of these 2 variables. Notice they're not even in the same units, I think. So that makes the interpretation of Euclidean distance here really, really tricky. You could think, well, maybe if I scaled this somehow different, they're all scaled here, right, to 0 mean 1 variance. So distance in that sense is in kind of like the natural units of each one of these axes. But it gets pretty hairy to say like, oh, this how is this different from that? In what way? I know this is not a very satisfying answer, but I don't really have a much better one. Okay, but the goal here was really not so much to focus on necessarily the specifics of this problem, but more on the mechanics here. I know that is the easy thing, so I'll go with that. The mechanics being you import some estimator from Scikit-Learn, And then you can call fit, you can call fit predict, depending on the problem that you're solving. Either it's fit with X and Y, or it's fit with just X, or it might be fit and predict with X. And this API is the same regardless of the estimator that you use. Let me get here to an important point, which is let's do this again now and refit our linear regression model. Now, instead of selecting 5 features, we're going to select 5, 10, 20, 50, 100, 200, 500, 1,000, and 1440. And we're going to fit them all again and again with increasing numbers of features. In every iteration through here, we will, we'll do this several times, 10 times for each one of these. Each time we will sample some of the features and we'll fit them all, and then we will score them all and keep that in results. And because this is linear regression, it doesn't really take that long. And then we can plot the results down here. Okay. Let's see, while this is running, what other questions do people have? Oh, this is taking longer than I thought it should. Maybe something is wrong. Maybe not.
I was able to run on my computer quite quickly, so.
Oh, here it is. There we go. Okay, this is the graph I was waiting for. Okay, so so it did complete eventually. And what you can see here, we have on the x-axis here, the number of brain features used, and on the y-axis, the explained variance as scored by this r². And what you can see that happens quite trivially, actually, is that the more brain features we use, the more accurate this is. And this is neat. So we got to, perfectly, by the time we're up at 1,000, we have perfectly accurate prediction of age from brain features. But, if we reflect on this for a little bit, things that seem too good to be true are probably too good to be true. And what we've encountered here is a case of overfitting. And we'll look at that in a lot more detail in just a bit. And I think it helps to address some of the issues that have come up here about, okay, how do we decide things? A lot of that is going to come from the way that we deal with overfitting. The problem that models, the more flexibility you give the models, the more features you give the models, the more accurate they're going to be in predicting data by definition. And that's called overfitting. Before I turn that, what other questions do people have here about the mechanics? Okay, so let's turn to overfitting. So, we saw that we can fit the data perfectly. And really the way to think about that is that we can overfit the data perfectly. Here, we're going to write a little function that will generate we'll look at this problem of overfitting in a lot more detail with some synthetic data. So here we're creating, again, a 2-variable data set, x, y. So here we're creating y as a function of x, and it's related to x through a quadratic with some noise. So here's a plot of one instantiation of that. We've set the seed to 10 in this case. If I set the seed to something else, we get another instantiation. If I set the seed back to 10, we get the same instantiation that we got before. We get 30 points. And suppose we try to fit these data with a linear model, we can fit a straight line to that. So here we're going to be using Scikit-Learn's linear regression. I'm fitting here. This construction here is just to make sure that this is the matrix has the right shape for this. I am running the fit. I'm running the predict here, and then I'm plotting the prediction against. I'm plotting a straight line. This is the original data, and I'm plotting a straight line to it based on this linear regression. And I'm plotting also the mean squared error. And what you can see is that the fit is not that great. So this is a case of what we might call underfitting the data. Right? The data has some patterns in it, and the linear regression is trying to capture those, but can't really because it's not flexible enough. Now let's instead use a very flexible estimator. Let's put a 10th degree polynomial on this data. See how well that does. So I'm gonna, along the way, I'm going to introduce you to a helpful little class in Scikit-Learn called a pipeline. The idea behind the pipeline is that sometimes you want your data and or your model to go through a set of operations while you're fitting it. For example, here we're going to demonstrate creating a pipeline that has polynomial features with a certain degree. So this is from pre-processing. We can create polynomial features, which may or may not include some bias term with a certain degree. So polynomial features are x, x squared, x third, x to the fourth, x to, and so on. And you can create these polynomial features with a certain number or degree. So that can be x to the up to x to the whatever the degree is. And here we're constructing our pipeline. So the pipeline object, what it does is it takes these kinds of inputs. These inputs are tuples. Each step in the pipeline has a name defined as a string, and then it has some kind of a scikit-learn, either what we call a transformer. These are sort of transformers of the data, or an estimator, in this case, an estimator. So the way to think about this is the data is going to come in, it's going to go through this transformer, which will expand the features to polynomial features up to degree, whatever the degree is. And then it will, basically x will go through this, right? So x will become, instead of x, it'll become x plus x squared plus, or not plus, it'll become x, and we'll add x squared and x third, x to the third, x to the fourth, and so on as columns. So this pre-processes our x up to degree. And then x and y will go through the linear regression after that. So this is the full pipeline that we get here. And this pipeline object has a fit, it has a predict. It behaves like a scikit-learn estimator. So if we create a pipeline that has several steps, we can, in one step, we can fit or we can predict using that, that full pipeline. Okay, so that makes the pipeline. So this whole function, what it does is it returns a pipeline object. Again, this pipeline object, you can think of it as an estimator, like the linear regression. It's notional. It hasn't seen any data yet. At this point, when we make it, it hasn't created any data. But instead, we can, so here we're creating a pipeline with degree 10, and then the pipeline is used to fit. So the way to think about that is it does the pre-processing, and then it fits. For example, if we gave it degree 10, it'll do the pre-processing of x to give us the polynomial features, and then it'll fit y to those polynomial features. And then we can use that to predict as well, given a set of coefficients that have been generated here. So here, the coefficients are generated. These coefficients are going to be, let me run this, and then I can show you that pipeline at this point has, it does not, it's a little bit more subtle than that. I think it's like that. Yeah, there we go. You can see that the linear regression has coefficients up to degree 10. So the way that this was constructed is that the pipeline, you can find individual items in the pipeline, you can find their coefficients, for example, or whatever their properties are, and it'll match the full set of operations that have happened here. So in this case, we started with an x that only had one value, and if we'd run linear regression straight on that, we would have gotten just one coefficient. But in this case, we ran it through polynomial features first, and then we got this set of coefficients. Okay, let's see how it did. It did pretty well. It fit the data. It even managed to hit this point perfectly with the polynomial of degree 10. Of course, when we look at that, we understand that this is not such a great model, and that's because, on paper, this fits really great. But if we had another instantiation of noise instead, now it fits terribly. So this is the same model fit to this original data, but now we've instantiated a new instantiation of this kind of data. We ran make x, y again, and we call that the test data. And on the test data, it performs really terribly. And that's because this model had too much flexibility. So our first model here was underfitting the data. Underfitting the data, not enough flexibility. This model is overfitting the data, too much flexibility. And that's a problem we'll encounter a lot of times when we do things. It's really what explains this performance as well. It fits the data perfectly, but it's overfitting to noise in the data. Okay, we can try to sort of sort through this a little bit. Maybe here we're making our pipeline. Now we're using degree 2 instead of degree 10, and that looks really nice. And we think that maybe if we did that, a lot of times, so here we've created a little widget. Here you can manipulate the order. Oh, sorry, this is the number of data points, and this is the degree. So you can see this is a training sample, and this is a test sample. The way this works is we only fit the model. The model, when it's fit, it only sees this training sample. And then we can look at this test sample, and we can vary the degrees. It's quite interesting, actually. It doesn't change a lot, even as we raise the degree of the polynomials until we reach, degree 7 or something. Now it starts to be really flexible. So this now it starts to be, and you can see how the mean squared error on the test set starts becoming really bad. At some point, it will go real terrible. Yeah, here we're fitting perfectly every point, but on the test sample, we're doing really badly at degree 20. We're getting so much flexibility that it fits almost zero error on the training sample, but really, really terrible error. So here, we've quantified error as mean squared error in this case. It was really terrible on the test sample. And you can run this multiple times with different seeds, and you'll see that it can be terrible to varying degrees, but it'll always be terrible in this case. Where if you went to degree 2, maybe it wouldn't most of the time it wouldn't really be terrible at all. And in particular, it'd be very similar to the training error, which is the training error. You can think of the training error as purely depending on the noise in the data. All right, the larger the noise is, the more this training error will be large, and this will be large as well. If we go the training error really small, now it's perfect, right? If there's no noise at all, and as we increase the noise on the training sample will go up, but particularly the noise won't go up more in the test sample than it is in the training sample. So it's kind of like a marker of a model that is neither underfitting nor overfitting. Okay, let's see. What questions do people have about overfitting? All right, great. And I assume some of you have seen these kinds of ideas before. Let's say how we solve this problem. Like, what is a set of systematic approaches to solving this problem? So we'll go to this next notebook here. And now we're going to talk about what we call validation, which is a way for us to approach this problem and try to solve it. Okay, so we're going to start with the Abide data set here, and we're going to talk about cross-validation. The idea behind cross-validation is that when we are interested in prediction, we are particularly interested not in prediction on the sample on which the model is fit. We are really interested more in what we call out-of-sample prediction or out-of-sample estimate of performance. That really gives us a sense for what's going on. And that's because of the dangers of overfitting. If our model allows for different levels of flexibility, and we don't know how much flexibility to endow it with, we might ask, well, how well does it do on this other set? And then titrate the level of flexibility that it has to improve performance on this other set. And that really cleanly deals with overfitting. The reason it does that is that overfitting is a case of fitting the model both to the data, the signal in the data, but also to the noise in the data. And the noise in the data is, by definition, the thing that is special about this sample. It's not going to be present in another sample, in another set of instantiations of the same process. So you can't, if you're looking at another set of observations, you almost by definition cannot overfit to the noise. So that's nice. And because this is such a central procedure in machine learning, Scikit-Learn implements a nice interface for doing that. There are various ways to do that within Scikit-Learn. One of the ways to do that is the train test split function in the Scikit-Learn model selection submodule. And the way that this works is you take, in this case, we've generated the same variables that we had before. Xall are all the free surfer variables. Y is the age. So we're going to use age as our target variable here throughout. And you give it that, and you then specify a training size. Here, in this case, it's specified as a proportion. And when we say that, what we say is take these variables and randomly select rows. 50% of the rows will go into what we'll call the training set, and 50% of the rows will go into what we call the test set. And split it up so that you match between X and Y, so that the samples in X that are going into the training set have a corresponding order with the samples in Y that are going into that test set. And then you get a variable here called split vars. In fact, the split vars is 4 different variables. It's X train, X test, Y train, Y test. Let's go back here. So just to drive this home, xall.shape is 1,004 rows, 440 columns. After running this train test split, we have now an X train that is 502 rows and 1,440 columns. So we've split this on the rows into 2 samples. And those 2 samples are going to be the substrate for our cross-validation procedure. So now what we can do is we can fit the estimator, our linear regression estimator, to X train with Y train. We're using the training data. And then we're going to use the score method twice. Once we're going to do that on the training data. And once we're going to do that on the test data. Now, here's a little riddle. Based on everything you've seen so far, what do you think that R2 train is going to be? Anyone want to venture a guess? I'll give you a hint. We've seen this result before, just a few notebooks back.
The 0.6 or the 0.2? I can't remember which one we're doing.
This is, notice here we are taking all 1,440, X-train contains all 1,440 variables in it. This is, okay, I'll go back to, where was it? We're up here somewhere. So it's going to be 1.0. It's going to perfectly overfit here. Because it has all those variables, and it has the flexibility to use all those variables to overfit, perfectly overfit to this data. I believe it'll be 1.0. We'll see. And then this, on the other hand, any guesses? This one's an interesting one. I don't know. We'll see, right? It depends a little bit on how badly we overfit, but presumably it won't be great. Yeah, it's terrible. It's bad. Well, it's negative. It's not that terrible. It's not that far from the mean, but it's negative. That means really, remember the definition of R squared. It means we should have just predicted the mean age here instead of relying on the data. We're really overfit, right? This is a clear signature of overfitting. In the training sample, perfect fit, meaning we hit every point, and that's because we had more variables than data. Now, that doesn't necessarily have to be the case. Even if we have more variables than data, we might not perfectly overfit. But in this case, if we did dimensionality reduction here, for example, we'd find that there are more independent variables. Even in the dimensionality reduced case, there are more independent variables than there are samples. That's why we get this perfect. We can hit every point in the data. And that'll often be the case in these kind of multi-dimensional problems. There are enough dimensions here to hit every point, even with the linear regression. And then in the test sample, it's terrible. Okay, so that is interesting. You might think 500 subjects is enough, but it's not enough when you have that many dimensions in the data. So then let's ask a different kind of question. What happened if we used less features? What would we do as badly? Okay, so here's another one for you. Here we're sampling 200 features from the original data, not the full 400. We're randomly sampling 200. And then we're train test splitting this smaller subset. Again, half goes into training, half goes into testing. And then we're fitting them all here with the training data. And then we're separately estimating R² for training, for test, and printing that out. Anyone want to guess what we'll get here? Oh, I'll show you the text after that. Hard to say.
They'll probably both be less than 1, but closer to each other.
Yeah, I think that's a pretty good guess. Yeah, there you go. So R² in the training sample is 0.79, right? We don't have, in this case, we have 500 samples, 200 variables, so we can't perfectly fit, unless for some reason this was like noiseless and this was the model that generated the data. But this is not the case here. And then R² in the test sample is actually better now. We had less variables, and we somehow improved the performance out of sample, which is an interesting kind of phenomenon. And there still is a gap, but at least we know now that the model is capable. And this is actually not a terrible. This is not a terrible model prediction. There might be reasons that are uninteresting why we get such model prediction from this thing, but if I did this here in the lab with someone and we did all the controls that we need and we got something like that, we'd be pretty happy with this number for most kinds of predictions that we do on a regular basis. So that's a good number. And so, okay, so this is the general procedure. We take the data, we split it up, we fit it to some of the data, and we predict on some other data in order to evaluate the model. And more generally, the procedure in general is called k-fold cross-validation. The idea is that we do this k times. Here we did it once. We split the data into 2. We fit on one and we predicted on the other. And then maybe if we wanted to be symmetrical, we could also we could fit to the train data and predict on the test data. We'd call that fold 1 and fold 2. And that's 2-fold cross-validation. But you could set that to other numbers. Here's a diagram that shows this with like 10-fold cross-validation. The procedure in general is defined as you define your number k, you split your data into k equal parts. In the first iteration, you use you use the training fold. You hold out, for example, here 10%, and you fit to the remaining 90%. You test on this. You make a prediction for this test fold. You iterate again. You take these 90%. You predict for that. By the time you're done here, one nice thing about this is that by the time you're done here, you have a prediction for every one of your data points that was obtained in a model that was fit in the absence of that data point. So you can actually get, for example, an R² on your full data set, where the prediction is, every prediction is done in the absence of the point to which you're comparing. So this is a fully cross-validated prediction of your entire data set. Because you've, at some point in time, every one of your samples was held out for this cross-validation. So here we go. This is k-fold cross-validation. And here's how that's implemented in code. Here we've implemented this with k equals 5. And here it's done really, really explicitly by really selecting at every point, randomly generating the indices and by shuffling here, and then sort of explicitly storing these things. Here we're doing, so we're doing this 5 times. This is the training R², and this is the mean training over the folds. This is the scores for the test sets. You can see it varies quite a bit between 0.43 and 0.62-ish. And this is the mean over all of those. So you can see there's still this gap between those. Generally, our mean training over in the training folds is a little bit lower. You can consider why that is. And overall, this has gone a little bit higher than it was before. And this is the thing that we really care about, is this mean testing R squared over the whole. So this is done really, really explicitly here. We used, Python's standard library, shuffling to shuffle, and then we did this kind of by hand. But you can actually do this really easily in Scikit-Learn, using this cross-val score function for model selection. It takes number 5. So this is the full call. This is kind of neat. You initialize an estimator object, and you pass this initialized estimator object into the function. And then inside the function, all this bookkeeping that's done here is done for you inside here. And you get, in R2CV, we'll see what that looks like. It basically tells you what the cross-validated R squares are for each fold separately. It tells you the full distribution, and then you can average that to get an average number that we got, which is very similar to the number we got over here.
So in the first one, you also got the training set R squared, which seems like it would be important for comparing how well the model does like overall versus in a new sample that it hasn't seen before. Like how do people usually use those values? Because it doesn't give you that in the second example.
Although to be fair, the thing we're really interested in is this thing, is this number. That's the number we're going to make decisions based on. We might look at this fit, the training error as well. Sometimes this gap is informative. It tells us a little bit about like, if we see that the fit to the train data is 1, then we know, oh yeah, we're severely overfitting here, and what strategy might we take? But usually, if in making decisions about model selection, for example, we'll really refer to this number. So this number is really the more important for us. But there are a bunch of other ways you can do this. So, for example, instead of doing this full bookkeeping that we do here, you don't have, if you want to know these things, you don't have to go through this full, very detailed bookkeeping. Instead, there is an object called kfold that instead of doing this full magical thing for you, which seems a little magical, it basically gives you, in every iteration through this object, it gives you the indices for that fold. So it gives you, if you ask for 5-fold, it'll give you in every iteration, it'll give you a random subset that corresponds to 20% of your data. And those will be, the 5 folds will be distinctly different from each other. So it does all the bookkeeping for you. It's very helpful that day. And then you can look for example, the training R squared if that's something that's important for you. I'm gonna skip over why cross-validation isn't the panacea, but we're going to go instead. One of the things I mentioned, that the result that we found may not be interesting. If you look at this, you'll see that if you look at this separately at this panacea, you'll see that part of the answer here is that the age distributions for different sites are different. And so if you can predict which site the data came from, you're already halfway or even more to predicting the age. So there's a problem with the data. And you need to think about your data when you're doing these kinds of things. That just because you got a good model prediction doesn't mean that you accounted for the thing that you're interested in, especially in neuroimaging. The confounds are many, and with human subjects, from my own experience, we try to predict a lot of things that correlate highly with age. And often we're very good at predicting age from neuroimaging data, but not a lot is left to predict after you've predicted age. At any rate, let's go more to sort of technical stuff here. One thing that we might want to do is might want to analyze our models in a little bit more detail, and Scikit-Learn gives us tools to do that. One of the tools that we have is the learning curve function, learning invalidation curve. So here's a learning curve. The idea behind this is we want to see how learning, given that we're doing 5-fold cross-validation, how does learning evolve depending on the number of samples that we're using. So that goes and does something like that for us. So the learning curve in general, the function learning curve in general, allows us to plot out, it gives us sort of the results, the sizes, the training scores, the test scores, everything that we need in order to analyze the performance. Again, this is a little bit of a higher level API, but it gives you what you wanted, which is the training scores and the test scores to evaluate, my model, in this case, a linear regression model, with this data on a series of, for example, train sizes. So here I'm giving train sizes is 100, 200, 400, just how many samples we're using. And notice within every one of these samples, we're doing further the 5-fold cross-validation. So here we're doing 5-fold cross-validation in 100 samples. That means we're doing the full, like, leave out 20, fit on 80, and then check on the remaining 20 and so on. So that's how we derive this. What we can learn from this, for example, is that if we don't have enough data, we're down here at 100 with, recall that we are using 100 variables here. So we're sampling out randomly, sampling 100 predictors. We're back in the situation 1 and 0. At 200, we're right where you can just almost barely predict. Again, remember, it's not, we have 200 samples, but because we've done k-fold cross-validation, we're actually not fitting to 200 samples, we're fitting to 160 samples. So that's why this is not 1 here. It's slightly less, but still there's a big gap. But as the number of samples grows, we're converging. So the way to think about this is how much data do you need to get these two things close to each other, given that you're going to use 100 features. Yeah, this I'm going to skip over that actually. And then another thing that you might do is you might look instead at the model complexity. So we're going to look at how this interacts with the size of the model. So there are two kinds of variables that we can factor in here. One is the number of observations on the x-axis, and then the complexity of the model. How many random features did we select to include in the model? And you see that things get a lot more interesting. This gives us a wider space of things to explore. We've also added error bars here. You can see that if you use only 5 random features, and every time we do the model fitting here, we select a different set of random features. Even with fairly few observations, there's not a big difference between training and test. And that doesn't change much with larger numbers. Here, we're back in the situation that we described in the beginning. Up here, we're sort of 1 and 0, and here we're converging. And so one thing to kind of look at here is, well, in the best case, when we use all of the data, where is the highest test R-squared? And it turns out that including 100 random features is better than including 30 random features or including 5 random features, even if, and only due to the fact that this point up here on the very right here is the highest point here. It's the one that gives us the closest, the highest R-squared. Again, whether or not this depends on interesting features in the data, things that are not related, for example, to the site is beside the point. For the technical issue here, is that this gives us a way to look at these 2 different dimensions of the data pretty systematically and select a model. For example, in this case, we would select a model that has more features based on a comparison of this to that. Okay, what questions do people have at this point?
I had a question regarding multi-collinearity. So some of the features that we're feeding in probably might be explained by one another, that there's a lot of redundancy. And I was wondering how this multi-collinearity comes into play with overfitting and this whole procedure.
Right. Yes. One thing that multi-collinearity will do is that depending on the noise in the data, so in linear regression will tend to happily include features that are linearly related to each other. And depending on the noise in the data, for example, it might take two variables that are really, really related to each other and enter them into the model with almost equal but opposite signs to get kind of the difference between these two variables, because the difference between them is going to be like something to really pay attention to. If let's say there are two variables and they're completely unrelated to your target, but they're they're collinear with each other, what the model might try to do is to get at the difference between them, which might be completely driven by noise, as a way to get some more variance explained just in the, or smaller error in the train set, and that's kind of a I'd say a pathological behavior of the algorithm, and the next notebook sort of deals with that a little bit head on. I see we're already running a little bit long here, so we might not get through all of that. Multi-collinearity is a huge problem for parametric or inference kinds of things, the kind of thing where you want to see one of these, where is it? This kind of thing, right? Multi-collinearity is going to be a huge problem for you in estimating, for example, the p-values associated with two coefficients that are collinear with each other. That's not generally the case for machine learning models, because if we have a way to deal with the collinearities some other way, like doing what's called regularization, which is to say I want a model that has that is as accurate as possible, but has as few features as possible also. Select out of these features as few features as possible to account for the data. Then as long as it's more accurate, we don't really care in some sense how it got to be more accurate. Does that answer the question, more or less?
Yeah, thank you for walking me through this. But wouldn't that regularization be applicable to both regression and classification, because you're reducing, the redundant features? So I wonder how multi-collinearity could just hurt regression, whereas it wouldn't as much in the classification world.
I think the same kinds of problems of overfitting generally apply in classification case. I will go in here just to show one thing, because I think it's such an important principle, and we've sort of almost touched on it, so I will show it, which is what's called the bias variance trade-off. And this one is this principle is a general principle in machine learning, regardless of if you're doing classification or regression, which is that your errors, so this diagram here, and demonstrates this idea. So there's a trade-off between the variance in your answers and the bias in your answers. One way to think about it is like this bullseye target practice kinds of things. You might have different models that have different characteristics. Ideally, your ideal model is up here in the top left. It's a model that has low bias, as in its predictions are always the errors mean zero, right? The predictions are always around the correct answer. And you can think of this both in classification and regression. It's easier to wrap your head around this in regression, but you can think of, for example, a low bias model for classification is one that doesn't prefer one class over other classes. But some of your error here derives from the variance in the results, right? So you might think of a model that has low bias. It's on average, it predicts the correct answer, but in practice, in different instantiations of the model, it predicts things that are far away from the correct answer. And of course, the worst case scenario is that it has high bias and high variance. But the really interesting case is this low variance, high bias case, because sometimes, in some cases, you can induce some bias into the results. You could say, never predict things that are higher than some value. And by inducing this bias, for example, by saying, never include more than 10 regressors in the final result, or include as few regressors as you can in the final result. This will induce a bias in the kinds of outcomes that you get, but it will also reduce the variance. And in fact, in some particular cases, reducing the variance in the results, even while taking the hit in the bias, might reduce your error. And in general, when you think about it, there is a general trade-off between bias and variance in machine learning models in general. Very complex models might have low variance, might have low bias, but because of their complexity and the flexibility that they have, their results, depending on what data you're currently sampling, might have high variance. And models with less complexity, when you're constraining their complexity, could have a bias that you're inducing in them, but might have lower variance. And depending, very much highly dependent on the situation that you're in, this trade-off, you might prefer the high variance, low bias case or the high bias, low variance case, depending on the specifics of the data that you're working on, specifics of the models that you're working on. We've gone a bit long here, but let's see. Can folks up for another 10 minutes of this? I'll just walk you through the ideas in this notebook in order to give you a sense, and then I'll show you what's in the 6th notebook, and then we can wrap up here. So this is really a fundamental idea to wrap your head around, and to help you wrap your head around this bias variance trade-off, I'm going to introduce you to the idea of regularization. So the idea behind regularization is that we're going to do something very similar to linear regression that we've done until now. But in addition to the ordinary least squares cost function, which is written out here in detail, the ordinary least squares cost function is find me beta coefficients, the coefficients on the features, such that the linear sum of the coefficients by the data is as close as possible to each one of the observations. And for each one of the observations, square that for me and sum that, and we call that the residual sum of squares. In addition to this residual sum of squares, I want one more condition on my solution. I want a solution such that the sum of the coefficients is as small as possible. And I balance these two costs, the residual sum of squares, which is written here on the left, with that through a hyperparameter called lambda. So one way to think about that is that if so long as the sum of this the sum of the coefficients times lambda is dominant in the equation, I'm going to try to squish this. I'm going to try to squish my coefficients down. I'm going to try to reduce their size so long as this side here is dominant, such that the residual sum of squares becomes the dominant factor in this. And this addition here, we think of that as an addition of bias. It pulls us away from the true answer, because the true answer in the data that we're fitting is over here. But we're saying, well, no, we're going to give an answer that's away from this true answer. And we're going to induce a little bit of bias. And we're hoping that by inducing a little bit of bias, we're gaining a smaller variance that will ultimately lead to smaller error. And we can test that using cross-validation. So this algorithm here, or this cost function here, is known as the Lasso regression cost function. And we're going to use Lasso here in order to do that. So the way this works here is we're taking, again, from Scikit-Learn linear model, this Lasso object. It's another Scikit-Learn estimator. We're going to scale the data. We're going to select 200 features as our starting point. But then we're also going to fit Lasso inside of this plot coefficient path. We're going to initialize an estimator with a certain alpha. Alpha is actually what is written here. Unfortunately, this is very confusing. The thing that is written here is lambda. In Scikit-Learn, it's called alpha. It's the hyperparameter that determines the cost on the addition of coefficients. And so we're going to try a bunch of different values of this alpha, which was lambda in the math, but here in the code, it's called alpha. We're going to pass that to our estimator. We're going to maybe pass some additional keyword arguments. We're going to fit that. and we're going to store the coefficients. And that's so that I can show you what Lasso does to the linear regression coefficients. This is to demonstrate what it does. That takes a little while, and here is the answer. So here, the x-axis is the value of this penalty, this lambda value here. How much are we constraining the values of the coefficients? Sorry, that was ridge regression. This one. Lambda sum of the, so we're taking here the sum. There's something closely related that takes the sum of the squares of the coefficients. But here we're taking the sum of the coefficients, or the absolute value of the coefficients. And so that's on the x-axis, is how much are we constraining the values of the coefficients? And then each line here is one of our coefficients. Remember, we chose 200 features here, so there are 200 lines here. This is called a coefficient path. As we go from the left, from small values of the penalty to larger and larger values of the penalty, what eventually happens is that all of those coefficients are squished. In the end here, we're basically, our model says, yeah, the regression coefficients should all go to 0. Here, we're basically predicting the average value. Again, we're doing age regression here. So in the end here, we're ending up with like, don't fit the data at all. Just predict the mean. Don't use these features at all. Just predict the mean every time. But along the way, what happens is that the coefficients, each one of them in turn, becomes smaller and smaller. And this is the effect of regularization. It has two potential outcomes here. One is the trade-off of bias for increased bias for reduced variance, which may reduce the error in the model fit. We have to test that using cross-validation. And the other effect of that is that the coefficients tend to go to 0, which is a nice property of this lasso. It selects variables for us. And so if we're up here somewhere with only very few coefficients that are non-zero, it also tells us which variables out of all our variables are interesting variables to look at. So it not only gives us a model that's more accurate, it also gives us a model that's slightly more interpretable because it does variable selection for us. Down here, this is contrasted with ridge regression, this other algorithm that penalizes, instead of penalizing for the sum of the absolute value of the coefficients, penalizes for the sum of the squares of the coefficients. And this one has a slightly different kind of behavior. In particular, it doesn't as nicely select variables for us because a lot of the variables are non-zero until they all go to 0 together. This is nice because a lot of variables go to 0 and then some variables are left. So it does variable selection for us. This one's not as nice because everything goes to 0 or everything is there. So it doesn't do variable selection. Now, so this is an interesting concept, this idea of regularization and how it relates to bias and variance. I'll just finish here with sort of showing you that, in fact, if you put your lasso into a validation curve, the idea behind this validation curve is take a bunch of parameters, like for example the alpha values, the cost function, this hyperparameter that says how much regularization you're going to put, and now do full cross-validation for me, 5-fold cross-validation, scoring it with an R2 score, do all of that for me, and then plot out here the R squared as a function of the penalty. What you might end up finding out is that there is, in fact, an optimum in this function. A good value of the penalty where the R squared actually goes slightly up. So just to set this out, R squared here is you get for the training data in blue, for the test data in orange. The performance of the ordinarily squared with this set of features is here in dashed horizontal line. So, out here, the penalty is so small that it doesn't really have any effect. The model behaves just like the ordinarily squares model. But as we go up here, the model starts to perform better than ordinarily squares. There's some gap. It gets closer to the performance on the training data, notice that the training performance always goes down. And that's because, you know, if the more flexibility we give the model, the more closer it's going to match the training data. So as we restrict its flexibility, the training performance is going to go down, even while the test data goes slightly up. Then eventually, both of them just go down to 0. Down here, the Lasso has constrained the weights of the coefficients so much that we're predicting the average always. And remember, R squared of predicting the average is 0. So we go to the kind of like the model that predicts the average down here at the end. But along the way, we hit a place where we've balanced bias and variance in a good way to find a place where inducing a little bit of bias has reduced our variance sufficiently in order to improve performance over, for example, ordinary least squared. So this plot sort of puts together a lot of the ideas we've seen so far. It uses cross-validation to do the error, both in training and test, and also applies this idea of regularization in order to improve performance a little bit. So this is one trick from machine learning in order to improve performances, cross-validation. Okay, let me stop here and see what questions people have. Okay, that was a lot. And I think it could be fun to, if these ideas are new to you, or even if they're not, to spend some time maybe during the hackathon exploring these ideas, either kind of deploying them to particular data sets, playing around with the abide data set or other data sets. A lot of what's tricky in doing machine learning in neuroscience is getting to the point where you have a nice neat table with all the features in there. So that's for example, I and people who work with me, that's where we spend a lot of our time is on what's called feature engineering these tables that we can run things on. So there's a lot of work to do there as well. I'll mention there is one more notebook here that you can study on your own, or we can ask questions on that. We can find some time to talk through this as well, where dimensionality reduction is applied in order to, prior to doing the model fitting. So you can do a step of dimensionality reduction followed by model fitting, and here it uses the pipeline object from Scikit-Learn to do that. Okay, so that was to summarize. And I'll give one more chance to ask any questions you might have at this point. All right, if no more questions, I wish you all a happy afternoon or whatever time it is where you are, and I'll see you all tomorrow or later today.